Well, it's a great pleasure to come all the way to Boston to tell you a little bit about the work that we're doing in the University of Queensland, and I'm very grateful to the organisers for the opportunity to come here. I'm going to tell you a little bit about a way of doing non-equilibrium dynamics in finite temperature Bose gases. It's sort of a method that we've developed over many, many years, and its application to a couple of particular problems, one at equilibrium and one in non-equilibrium. I'd like to acknowledge all my co-workers who are listed here on this particular project. Really the talk is split up into three parts. So, like I said, I've been working on this classical field method for Bose gases for quite a number of years. So I just want to, I realise that most people in the audience probably aren't familiar with this. So I just want to go through some simple outline of how the theoretical method works. Basically, it's a way of using the Grosspiesky equation for finite temperature systems. And then we're going to talk about a little bit about applying it to superfluidity in two-dimensional Bose gases on finite-sized two-dimensional Bose gases. And then something new that we're really getting, well, we've just started getting to recently, is simulating sort of steady-state non-equilibrium systems in ultra-cold gases. So I want to start out by telling you about classical limits of Bose gases. So normally when we talk about classical limits of quantum statistics, we normally think about the Maxwell-Boltzmann distribution. And this is sort of the particle-like classical limit of quantum gases. So this is when the temperature is much, much larger than the energy of the modes that are occupied. And so when you take the Bose-Einstein distribution, you take the Maxwell-Boltzmann limit, and you just end up with the standard Boltzmann-like factor. And so in this limit, really the particles are behaving like billiard balls. It's that nice picture from undergraduate statistical mechanics. And if you want to describe the dynamics of the system, then the equation you should be looking at is the kinetic equation, or the Boltzmann equation. However, there is another familiar limit, or classical limit, which is more familiar from light rather than particles. But if you go to the limit where the temperature is much larger than the energy of a mode, then if you go ahead and expand the Bose-Einstein distribution here, you use a Taylor series expansion on this exponential, and what you find is you get 1 plus energy over kT plus lots of other terms minus 1. You see the plus 1 and the minus 1 cancel to give you this distribution here, which hopefully you'll recognise as being the equipartition distribution. So usually I guess we're used to thinking of this without the chemical potential. So if we're dealing with photons, then of course the chemical potential is 0. But if we're going to deal with matter waves, then we're going to need to leave that in there. But basically, the idea is in this wave-like limit, rather than treating atoms as particles, you need to have some sort of wave equation. And what's the wave equation that we know for both condensates? Well, it happens to be the Grosspiesky equation. So normally, it's commonly argued that the Grosspiesky equation is only valid for Bose gases when you're dealing with a T equals 0 Bose-Einstein condensate. And I guess the point of what I'm going to tell you a little bit about is you can actually also use it for finite temperature Bose gases as well. Now, why isn't this, why doesn't people realise this for a long, long time? Well, the problem is that with all classical equations of motion, there are problems with classical limits. So, not being very clear here, I guess the thing is, if you think about blackbody theory, okay, the theory of blackbody radiation, if you go ahead and apply classical physics to try and understand what that should look like, you end up with the Rayleigh-Jeans law. Well, that works quite nicely for very low energy, long wavelength modes. It doesn't work for those short wavelength modes. And so they're exactly the modes where the Bose-Einstein distribution is actually important. And so what's the thing here? Well, this sort of classical physics approach is good for when there's a large number of particles per mode. Okay? And so if we go back to this expression here, it corresponds to there being much, much more than one particle in mode with energy k. Now, if you just simply go ahead and apply this classical theory to all modes, you find that if you say, okay, my equilibrium particle number is given by this expression here, you go and try and calculate all the particles in your field, you find that it diverges. And so the problem is that you need to only treat a finite number of modes as being classical in nature. And so the solution to try and use classical field theory for finite temperature Bose gases is to implement a UV cutoff. So the Bose-Einstein distribution has some modes that are very highly occupied down at the lowest energies, but as you go to higher and higher energies, the occupation numbers dip below 1. And so you really only want to apply this sort of classical field theory to those modes which have a very highly occupied in equilibrium. And so the way we did this was by implementing a ultraviolet cutoff in the description of the Bose field. So you split it up into a classical part and a quantum part, and then only describe the classical part with your Gross-Podolsky equation. And so what I've written down here is simply the usual Gross-Podolsky equation, but it's got this projection operator out the front. And all this does is it takes some object, projects it onto a basis, and then only retains those modes in that expansion, that classical nature. So this notation here is saying, let's keep all wave numbers in a particular region of phase space which have a highly occupied equilibrium. Okay. So this is something we've been working on for a long time, and so back in around 2000 or so, we started looking at this equation for the first time. What we did is, instead of trying to represent an entire Bose gas using classical fields, we just take a finite region of momentum space, and we start off a simulation with a fixed energy and a fixed particle number in 3 dimensions, random distribution, and just see what happens. And so what you've got here is a plot of the dynamics versus time. In particular, we're plotting the occupation of the condensate mode as time goes on. And each of these curves here is for a different initial energy, or a different initial state with different energies. And what you find is that for the lowest energy state, you end up with quite a large condensate fraction. And as you go to higher and higher energies, the condensate fraction goes down until once you hit a certain, a large enough energy, then you see no condensate fraction equilibrium. And so it really looks like the reversible Gross-Podolsky equation is describing some sort of relaxation dynamics. Now, if you go ahead and look at what's happening from here on, from sort of the time that's equilibrated onwards, you can go ahead and what you find is there's lots of fluctuations going on, but there's sort of a very well-defined thermal equilibrium. And if you go ahead and look at the distribution of the momentum modes, over here I've plotted the average quasi-particle distributions for each of these various energies. And what you can see here is this looks very much like an equilibrium distribution, and what you can find is you can actually go ahead and fit one of these equipartition occupation distributions to these curves and extract a temperature for the system. So it very much looks like this sort of simplified toy system, I guess, with this finite number of momentum modes is evolving towards equilibrium. Now this is perhaps a slide I should have had a little bit earlier. So when is this sort of classical field theory applicable for finite temperature Bose-Einstein condensates? So I was trying to say that it's only valid for when you've got modes which have a large occupation number. And so what I've done here is plotted out some curves for a system of rubidium-87 atoms, 2 million of them in a harmonic trap of 100 Hertz. So sort of typical numbers for an experiment on BEC. And along this axis here, I'm plotting the mode occupation of a variety of modes. The blue curve is the BEC mode itself, and each of these curves down here is the occupation number of a particular excited state in a harmonic trap. And so the critical temperature is this red line here. This is just all to ideal gas, by the way. It hasn't taken into account interactions, but the picture doesn't change quantitatively. It doesn't change qualitatively. And so remember, the important thing is that for modes to be treated as being classical, they have to have a large occupation number. Okay, so this is where the Rayleigh-Jeans limit is appropriate. And each of these modes here is plotting the 10th excited state, 35th, 120th, 600th, and 2000th. And this is not talking in terms of h bar omega. This is talking in terms of the total number of harmonic oscillator states up to a certain energy. So this mode, the 2000th mode, is something like 20 h bar omega or something like that. It's just trying to sort of quantify the number of modes in the system that are classical. And so what you find is, at the critical point, 2,000 modes of the system have more than 5 atoms per mode. And so there's quite a large fraction of the system can behave classically. Now, all the modes above that are starting to have small occupation numbers, so you should be treating them in a different way. But the point is here that if you look over this temperature regime here, there's a significant number of modes. I guess down here, there's 120th mode is dropping below 5 particles per mode. But over this large temperature range, there are a significant number of modes in your Bose gas that you can possibly treat as being classical. And so I would argue that over this temperature regime, from somewhere near half Tc to a little bit above Tc, this sort of classical field approach to Bose-Einstein condensates can be quite useful. Well above Tc, the occupation numbers drop away very quickly, and you're back in the regime of kinetic equations. And once you go down below about a third or 0.2 of TC, you're not left with many thermal atoms at all, not many classical modes, apart from BC itself. And so this is typically where you'd think that the T equals 0 GPU is appropriate. But over this regime, from some fraction of TC to around about TC, there's a large range in which finite temperature GPU is appropriate. Okay, so that's sort of a very, yes? Yeah, so the idea is that this is a regime where you might be able to do some useful physics with classical fields. Okay? Now, all that I've said is very much hand-wavy, phenomenological sort of argument. You can actually go ahead and put this on a much firmer foundation. And I guess the other thing is I've also only been focusing on this classical regime where you've got to also worry about that other part of the gas as well that you're not describing with classical waves. And so with... yes, certainly. So the S and the P stand for stochastic projected Gross-Pilecki equation. Okay? So the projected is the idea that you're just representing part of your system with the classical field, and the stochastic part has to do with the fact that you're including or trying to incorporate a connection to those other quantum modes of the Bose gas. So this is the idea. You split your system into a classical part and a quantum part, and then you can go ahead and derive a master equation using quantum optics methods for this classical region. You make this high temperature approximation, which essentially has to do with making the classical approximation for those low energy modes. And then you can make use of sort of techniques from quantum optics to derive a Fokker-Planck equation for the Wigner quasi-probability distribution for the system. And what you find is this has a corresponding set of Langevin equations. And the Langevin equation you have is essentially a Gross-Pilecki equation, but with some stochastic terms that represent the coupling of your classical fields to the rest of the gas. And so the sort of standard theory that we've written down is it takes all these quantum modes up here and treats them as a reservoir with a chemical potential and a temperature. Okay, and this results in particle transfer back and forth with your classical fields of the gas. And so you end up with a Gross-Pilecki-like equation with this start down here, and you can just treat this as a reservoir. Now, you don't have to do that. You can actually go ahead and derive a kinetic equation for this reservoir if you like, and you have lots of complicated coupling terms. And that is something that you could do in principle if you wanted to describe the full dynamics of a Bose gas, but it's pretty complicated, and we haven't got all around to doing that. And I don't think there's all that much new physics that you're going to get out of writing down such a description. Okay, so at the risk of scaring everyone in the audience, this is a sort of standard equation motion. You don't need to worry about the details too much. But basically, the top line here, this LGP is the normal Gross-Pilecki operator. And so the top line here is simply your usual Gross-Pilecki equation. It's got this projection term at the front that keeps you just dealing with the classical part of the gas. And then there's a couple of two coupling terms that describe different types of collisions between those particles in the thermal cloud and the particles in your classical field. There are collisions that take two high-energy atoms and transfer one to the classical field region. We call these growth collisions. It ends up with a term that looks like this. You can see, the important part really is that you can see there's a chemical potential here and there's a temperature here. This term here is just a collision integral. It gives an overall rate of the process. But what this means is that the classical field sort of grows or shrinks depending on what the chemical potential and the temperature are of the connected reservoir. And this is a sort of effective noise term that goes with that due to the fact that there are continually particles going in and out of the gas. The second term here has to do, we call a scattering term, and it's a similar sort of thing, except this time you've got a high-energy particle pushing around one of the particles in the classical field. Now, we've used this for a variety of different things. Actually, I'm getting ahead of myself. I will go on to the next slide. So one of the things you can do, so as I was pointing out, you have this chemical potential and a temperature in here, and so what you find is this equation, once you put in any sort of random initial conditions, it will evolve itself to some sort of equilibrium state, a little like what I showed you on the slide with the sort of toy model that we had. And so what this means is this approach is actually quite useful for looking at thermodynamics of interacting Bose gases. It's got the major advantage that it's non-perturbative in particle interactions, and also the way it's set up, it's entirely independent of the computational basis. So you know there's this cutoff between the classical part and the quantum part of the distribution, But what we find is if you choose that cutoff over quite a range, you find you get results that are essentially independent of what that cutoff is, which is good because we're trying to describe the universe rather than some model. And so you can go ahead and incorporate that part that you've eliminated from your equations using Hartree-Fock theory. So that should be pretty good because it's all a relatively weakly interacting system. And you go ahead and apply it to a variety of problems. So for example, we have applied to the shift in critical temperature in harmonic traps, not Zoran's experiments from more recently, but many years ago, Alain's experiments back in Orsay, they measured the shift in critical temperature, and we applied our theory to those experiments. It's also been used for looking at correlations at finite temperature, but one of the really interesting or regimes of interest is for low-dimensional systems. So in three-dimensional Bose gases, physics is relatively boring, and it's all relatively well described by mean field theory. But once you go to two-dimensional, one-dimensional systems, then fluctuations are pretty important. And in the infinite systems in the thermodynamic limit, they actually destroy condensation. And so this is one of the areas that we've been trying to explore. And so I'm going to spend time is not doing so well, so I'm going to quickly go through some of the stuff that we've been looking at with two-dimensional Bose gases, but I want to get onto the non-equilibrium stuff, so please excuse me if I skip through it fairly quickly. Okay, so when you're calculating these thermodynamics, so the basic idea is you can set your thermodynamic values, your mu and your t, and you solve your equations in time until you reach equilibrium, and then you can go ahead and calculate various correlation functions. So for example, one of the correlation functions that's of interest is a single particle reduced density matrix, and you can go ahead and use this to calculate the condensate fraction using the Penrose-Onsager criteria. So this is just a matrix you can go ahead and diagonalize. If you look for the largest eigenvalue, then it tells you what your condensate fraction is, and also gives you a condensate mode shape. You can also do things like calculate higher order coherence functions. Now, one of the things we've looked at recently is looking at sort of beyond Gaussian fluctuations in the system. So because the equation is non-perturbative in particle interactions, you actually see effects sort of going beyond Bogoliubov theory. And so by defining sort of a number-conserving non-condensate operator, so it's basically a formal way of taking a system and saying I've got a condensate part and I've got a non-condensate part. You can then go ahead and calculate correlations of your non-condensed particles, and in particular calculated sort of second-order moments and third-order moments. So these are things that would be zero in HFB theory. And so this figure up here, I guess the black line here is just indicating, so this is for, I should go back a bit, this is for a harmonically trapped system. The black line is sort of indicating what the condensate mode would look like at equilibrium. The blue line is calculating what the non-condensate would be. And then this red line here is something that's called the anomalous density, and this is sort of evidence of many-body interactions in the system. And so this is sort of, well, I'm highlighting this because this turns out to be important in two-dimensional systems. Okay, so again, like Zoran, I was trying to pack too much into this talk, so we're going to have a look at this part relatively quickly. So as I said, BC and 2D, Penrose-Onsager says that Bose-Einstein condensation occurs when there's an eigenvalue of the one-body density matrix that it's extensive, but that's not the case in 2D. What you find is that for a finite-sized system, you will have a macroscopically occupied mode, but if you take the size of that system larger and larger and larger, the n0 that you get decreases and decreases until it hits zero in the thermodynamic limit. However, you do have a superfluid phase transition. It was pointed out by Kossler, Salas, and Berezynski, and these guys here came up with sort of the dimensional number that tells you what the critical point is for a 2D Bose gas. Now, this is for a system in thermodynamic limit, but in the lab, of course, we're always dealing with finite-sized systems, and so one of the things that we're interested in, what's this connection between Bose-Einstein condensates, Berezynski, Kossler, Salas physics, and 2Ds, in finite-sized systems and an experiment. And so there have been lots of experiments done on this, a number of people who are here in the audience, but I guess we're just trying to go back and do some naive calculations and with this classical field method and try and understand the connection between these various things in very simple language. So given the time, I actually think, well, okay, so very quickly, So we went right back to the homogeneous Bose gas, and we took the experiments of Zoran and Jean Dalibard and just took the parameters that they were looking at, but simulated a homogeneous system just to try and understand this separation between BKT and BEC physics. And I guess one of the things that we're hoping that we'd be able to simulate larger and larger systems and see a divergence between the BEC point and the BKT point, because the BEC temperature should eventually go to 0. Now, we were perhaps a little bit naive because you actually need to go to huge systems before you actually see the separation. And so what we found is that the condensate fraction and the superfluid fraction basically always coincide in the system. But we did find an interesting point that, well, it does appear that the condensate actually still goes to 0 relatively smoothly, but this anomalous density actually drops, it seems to drop at exactly the same point as the superfluid density. And we've actually gone ahead and done a little bit further analysis of this sort of thing, looking at these these anomalous correlations, that because I'm running short of time, I think I'm going to skip over this. But we looked at sort of the particle hole structure, the quasi-particle nature of the excitations. You can characterize these by sort of looking at the U and the V components of this generalized density matrix. What we found is there's actually a very, very sharp transition. So this is as you're taking a fixed density, as you're increasing the temperature, and look at this sort of this Bogolubov quasi-particles, and what you find is you go to the transition point, the sort of non-zero, then all of a sudden they simply drop down to 0. And so this is something that we're sort of following up as a signature of the transition in the finite size system. And if you go to, no, I won't even say anything about that. Okay. So also associated with two-dimensional systems, one of the things we're interested in is trying to look at the superfluid density in a non-uniform system. So most of the stuff that has been done has been using this result of Prokofiev and Svistanov and sort of using the local density approximation. So once we're above a certain density, then a certain fraction of the system must be superfluid. Now, how does this work away from the local density approximation? Well, we're interested in trying to quantify superfluidity in another manner. And so we were looking at systems in a quasi-2D toroidal trap, and the idea is that we basically try and make use of the fact that a superfluid has persistent flow and try and work out what the superfluid fraction is from this persistent flow. So the idea is we start with a system with a singly charged vortex in here that's rotating, and then couple this to a stationary thermal cloud. And the idea is that any superfluid fraction is going to keep rotating around this point, whereas the thermal cloud is going to rest all of the normal fluid. And by making a comparison between these two, you can actually calculate what the superfluid fraction of this as we change the temperature, for example. And so the idea is that we go back to this sort of stochastic reciprocity model. We have the classical field description for this region here. We started off rotating, but then this thermal cloud that's connected to has no rotation, and so it's going to try and damp the system down so that the normal cloud is stationary. And so we've done this. What we find is that there is remains a persistent current in the system, and we can actually go ahead and make use of the fact that there's a velocity field identifying a superfluid, and go ahead and calculate the difference between the condensate, the superfluid fraction, and what the total density is here. And so what we find is that the condensate is sort of dragging along some fraction of the quasi-particles, and so the superfluid density is larger than the condensate. Now, this is still work in progress, so I haven't got too much more to tell you about that. Okay, so in the last few minutes, I want to tell you about the most recent thing we've been doing, which is non-equilibrium transport. So if you remember back to the equation that I showed you before, it had a chemical potential and temperature in it. And as I wrote it down, they were just global parameters. But you can also imagine situations in which you have different thermodynamic parameters in different parts of the system. And so there's been a recent experiment on this sort of thing done by Tillman-Esslinger with a degenerate Fermi gas, where he's created this very complicated, looks very complicated to me, trapping potential, where he split his Fermi gas into two different regions and put a channel in between the two of them, and then essentially shifted the relative height to induce a chemical potential difference between the two sides, and then studied the flow from one side to the other, both in the normal gas and superfluid regimes. Also, there's been another experiment by Dana Anderson's group at Gila in Colorado, where working with the BEC and atom chip, and what he's done is, well, in these experiments here, he started off with a condensate and then sort of moved in these optical beams from the side and shoved all the atoms over to the left, And while they're continuously evaporating here, particles are sort of traveling over these barriers onto this side of the trap. And on this side of the trap, he's got a beam that's blasting away any atoms. So essentially sitting with a reservoir over here, and no reservoir over here, it's essentially vacuum, and studying the flow from a region where there's some thermodynamic parameters to something where everything is zero. Now, another experiment that you might be familiar with from helium, or from superfluid helium, is the superfluid fountain effect. So this is the same sort of idea. So here we have a superfluid helium bath. We have a section up here where we apply a heater, so it creates a temperature gradient between this part of the system and here. And this has got a plug in it that only the superfluid can go through. And by heating this part of the system, essentially you're lowering the chemical potential, and that creates a gradient, which means that the superfluid flows up through here, and the pressure difference can be large enough that you actually see quite an impressive looking fountain. Now, some people, the Polish group have been thinking about this in terms of Bose-Einstein condensates. Their idea is that the same sort of thing. You have two different traps where you have a hot side and a cold side, and if you make a channel in between them, they've studied the dynamics of how the condensate behaves, and what they find is that the condensate sort of starts oscillating back and forth between these two sides. Now, I thought this was a really interesting idea for an experiment, but the thing that bugged me about it is that it's a transient nature. So you start off with the hot side and you start off with the cold side, and then you sort of look at the transient dynamics as you go, as you connect the two. Whereas something that might be more easier to deal with, theoretically at least, is if you try and establish two different reservoirs that have fixed temperatures and then study the dynamics between those two fixed reservoirs. So this is called internal convection in terms of superfluid helium. So a similar sort of thing before, except rather than having a super leak, you actually have a macroscopic channel between the two sides. And if you maintain one side of the system at a higher temperature to the other side, what you find is that the normal component will flow from the heater through to the cooler side, and the superfluid flows back and forth. And so you can kind of think of the superfluid going from here to here, being converted to normal fluid and going back, and it's sort of going back and forth. And this is this idea of superfluid convection. Now, this idea, I won't mention that, but this idea was picked up by James Anglin, one of his PhD students. And so they came up with this ring with the Bose-Hubbard model where they had a hot bath and a cold bath on each side of the system, went ahead and derived a master equation and tried to analyze it in terms of Bogoliubov theory. And so what they found is that they got a current of condensate from one side to the other that scaled as a difference in temperature between the two sides. Now, the thing about this calculation was that it was using Bogoliubov theory, and so it was basically in the collisionless regime. Whereas where I picked up interest in the matter is what happens once you go beyond the collisionless regime and you have interactions between the normal fluid and the superfluid as they flow past one another. And what's going to happen? Well, in superfluid helium, as you do this experiment, what you find is if you have changed the temperature between those two sides, then at a certain temperature or flow difference between the two, you end up with superfluid turbulence. And here's some simulations that have been done. So firstly, with the vortex filament model by the group of Subota, done very recently, trying to look at this in superfluid helium. He's also looked at when you have a two-component BEC, we take two different atoms and you simply put them flowing through one another, and beyond a certain speed difference, then you start to see this propagation of vortices. Now again, this calculation here is also a transient calculation. They start off with their BECs flowing against one another and see how it decays. But with a stochastic GP model, the idea is, rather than show you that, I'll just go to first slide of the results. The idea is that if you have two different if you have a system, say, of rubidium atoms and then a reservoirs, say, of potassium atoms, and you have two different you have reservoirs in different regions of space at different temperatures, then you set up a non-equilibrium steady state. And so we've just been starting to do some sort of calculations like this. It involves extension of the formalism that I described before, but it's not too difficult. But the idea is here, this is just a one-dimensional calculation. So this is space along here and time along this direction. And the idea is that it's periodic boundary conditions. That's something else that's very important to note. This is simply for computational convenience. But we define the region at the edges of the trap as having connected to a hot reservoir. In the middle, it's connected to a cold reservoir. And so there's exchange of energy happening here and here, but in between, there's no exchange of energy between the reservoirs and the system. And so what I've done is to start off with a zero temperature initial condition and then let the system come into equilibrium. What you find is you can see sort of all these sound waves propagating back and forth between the two reservoirs. But you can see in the cold region there's relatively little noise, but in the hot region there's quite a lot of noise. So that's an indication of the temperature difference between the two sides. And so if you go ahead and sort of let this come to some sort of steady state, you can go ahead and perform Penrose-Onsager analysis of what the condensate looks like. And what you find is if you plot the condensate phase, then you find that it's flat in the regions of the reservoir, but there's this gradient in the two regions between the two reservoirs. This is indicative of a superfluid flow from one side to the other. Now in this calculation here, the condensate fraction of the system was something like 85%, so it was really quite cool, and it was almost certain that this was in the sort of collisionless regime that the perturbative calculation by James Anglin was done in already. Where we want to go, though, is beyond this perturbative regime and where there's other things going on. And so my expectation is as you increase the relative flow between the normal and superfluid components, you'd start seeing formation of topological defects, for example. And so this is an example of a calculation where the condensate fraction is lower, and here you can start to see solitons turning up in the system. Now, we haven't run these calculations long enough to do an analysis of what goes on, but I'm hoping to see some sort of one-dimensional version of turbulence in the system. And so where we want to is go beyond 1D into the two-dimensional and three-dimensional regimes, and I think that's where it's going to get really interesting, because at a certain point we should see this steady-state superfluid turbulence, and in particular in 2D, I don't think there's been much work done in 2D superfluid counterflow turbulence. Not the least because I think the experiments are very hard to do in superfluid helium. And so with that, I apologise for my overestimate of what I could squeeze in. I've given you a little bit of an introduction to this whole idea of classical fields for BEC, when they can be useful, and what the approximations go into it. Told you a little bit about the differences between BEC, BKT, and superfluidity in 2D systems, and just showing you the sort of direction you want to go in and looking at non-equilibrium steady-state physics using classical fields. So with that, I'll thank you for your attention. No, I didn't. So the color scheme here, so this is simply the density. And so it's quite a large, this is basically constant density with fluctuations on top of it. Sorry about that.
I was wondering, is there back action included between the modes that are not in the condensate and the condensate itself? Because I'm hoping for some back action to, for example, fill in things like solitons or certain regions. I'm interested in that. To make soliton propagations slower, this kind of stuff.
Yeah, so that's a good question. So yes, there is. So the whole idea of this classical field is that your classical field is not representing just the condensate. It's got the condensate plus the low lying thermal cloud. And so the stuff that's eliminated, there's no back action with that, but the modes that are important for the back action are all the other low-lying ones, and so yes, they are included.
Two quick questions. One actually maybe connects to this about the low-lying modes. If you go back to the graph of applicability.
Mm-hmm.
I mean, if I understand that for you as a total number of states, it makes a complexity. But the experimentalists sort of take the third root of these numbers, roughly, right?
Yes, that's right. That's right.
And so I was wondering, how big is actually the effect of interactions on this, right? Because I think the third root, I get down to 10 h bar omega, mu is bigger than that in interacting gas with significant condensed fraction, right?
Yeah.
So say ideal gas mu is negative, I don't know how much. Interacting gas mu is like 10 h bar omega, right? You can make a big difference on these occupations.
So I'm talking about the difference between mu and the highest excited state. So you need to shift everything up by that chemical potential. Yeah. Okay. So I'm talking about a difference of 20 h bar omega or 30 h bar omega between the chemical potential and the...
Okay. And with that definition, you think it doesn't change qualitatively?
Yeah, that's right.
Otherwise, it really changes qualitatively.
Yeah, no, that's right. That's right.
If I take the okay. And my second question was on a different part of the talk, which is, can you tell us a bit more about this anomalous density? What is it experimentally, and what do we do? It's an interesting thing to check.
Right.
Is it just the explanation value of psi or something?
Yes, that's exactly it. That's exactly
what
it.
do we measure?
What do you measure? That's...
Some interference experiment?
Well, so I'm not 100% sure, actually. So I guess this has got to do with it's particle-particle correlation. So you sort of have condensate atoms coming in, sort of creating opposite excited states and coming back to one another. So the net effect in equilibrium is that I didn't leave the slides in, but it sort of reduces the sort of effect of condensate-condensate interactions. So yeah, maybe we should talk about this later.
There was a correlator, two correlation functions at the bottom of your equation. I didn't know what those. There was a
Yep.
slide ahead of here. I think it's like EW sub n.
Oh, yes. I know the one. These ones here. Yep.
Yeah.
So these are the correlation functions of the noise that goes into this equation here.
What's the difference between the G and the N?
So there's noise associated with these the collisions here, these gross collisions, and there's also noise associated with the scattering collisions. So you can see this noise is associated with this term, and this noise is associated with this term.
I am interested in the, well, I don't know if we should call it second order or fourth order, the correlation function, but anyway, G2, okay, which is fourth order.
So two is
Yeah.
the hint.
Yeah. I'm not responsible for that, okay, Mando is responsible for this, or Glauber, or whoever. You mentioned at one point you show a graph and say correction beyond the Gaussian.
Yes.
So do you mean that your theory first gives the factor of 2, the Ambry-Brown?
Yes, it does. Yes.
And then this beyond.
Yes.
Well, the reason why I'm really interested, and I would like to have your comment about that, that, as you know, I have been always very interested by the significance of Ambry-Brown twist. And many people say that Ambry-Brown twist is related to the bosonic enhancement or something like that. But on the other hand, we know that with classical light, provided that it is incoherent, we also have the factor of 2. So I'm personally convinced that there is not so much of bosonic stuff in Ambry-Brown twist. It's rather a matter of Gaussian fluctuation. Would you say that your approach supports this interpretation?
Well,
I can show you detailed calculation.
yeah.
Privately to show you why I claim that it has to do with Gaussian fluctuation.
I'm not sure. I guess my impression, well, the one thing I would say is that this is all a theory of classical Bose fields, and so the fact that it's classical is due to the fact that it's bosonic.
Yeah, sure. Okay, yes, of course. You cannot have classical light waves if it is not boson.
Yep.
But once you have said that, you can totally forget about bosonic enhancement, the usual notion of bosonic enhancement.
Yeah, I'm not sure if I have a clear picture on that in my head, but I'd be very happy to talk some more.
This is maybe a good opportunity.
Yeah.
Just a quick comment.
Go ahead.
Sorry. The time-time correlate is a particular type of the second order correlation function.
Yep.
You call it second order.
It's a second order because it has 4 quantum fields in it. It's a correlation between a state with 4 particles in the condensate and 2 particles in the condensate.
Yeah.
And 2 particles out.
So this is what we're trying to show here.
One of the most interesting, but it is a type of second order correlation.
I was wondering if you looked at the transition between, the actual BBC transition in a trapped two-dimensional gas and the VKG transition that you get the trapped two-dimensional gas once you put an interaction. Because I guess you don't make the LDA, so that the...
Right. So this is sort of one of the things I guess we're well. So we have looked at this stuff before. There's a couple of papers on it, but I guess the thing is that the thing that was done in those papers that I'm I guess slightly unhappy with is that you sort of say, okay, my density profile looks like this, and once we hit this point here, then this is where it's superfluid, and so you sort of have this very sharp Thomas Fermi-like superfluid. And so I guess the idea of what I was trying to talk about today is we want to look at beyond LDA in that respect. Okay. So it's still a work in progress.